Good morning all of you. In the last class we are discussing about the technique of calculus of variation, and we have given two examples. First one is the minimum distance between 2 points, that is the equation of a straight line. It is derived by using the technique of calculus of variation, and the second example we have done is the equation of catenary, that is the minimum surface area taken by a curved path. And one more example we are doing now. The third example is called Branch-Stockron problem. That is Branch-Stockron problem. Don't be afraid of the name. It is a very simple thing. That is when a body is moving from one point to another point. The problem, Branch-Stockron problem, means when a body moving from one point to another point, from 1 to 2, under the influence of gravity alone, only the force acting is gravity, and we have to find the minimum time taken. The minimum time taken for a body to move from one point to another point under the influence of gravity. That is called, the solution is called solution of the Branch-Stockron problem. Now consider the body is moving from 1 to 2 within a time t from 1 to 2, and to solve the problem, consider a small portion of this path, that is equal to ds. As in the previous case, we can write ds is equal to dx square plus dy square square root of dx square plus dy square, and we know that time taken is equal to, let dt be the small time taken for this much displacement. Dt is equal to displacement dx divided by velocity v. Dt is equal to ds divided by v. ds divided by v, that is equal to square root of dx square plus dy square divided by what is velocity. We can take the equation. Kinetic energy is equal to, at equilibrium, kinetic energy is equal to potential energy. Half mv square is equal to mg. We can write x, mgx. Kinetic energy is equal to potential energy. That is m and n getting cancelled. V square is equal to 2gx, or v is equal to square root of 2gx. Therefore, divided by, we can write square root of 2gx. That is equal to square root of d. This can be written as 1 plus y dot square into dx divided by 2gx. This is the equation of the time taken, and the total time taken is equal to integral from 1 to 2 square root of 1 plus y dot square divided by 2gx into dx, or this can be written as integral from 1 to 2 f dx, as in the usual form f dx, where f is equal to square root of 1 plus y dot square divided by 2gx. If it is needed, we can avoid 2g. It is a constant, it can be avoided or can be kept there. This is the value of function, and in order to find the minimum path, in order to find the minimum time taken, t to be minimum, what is the condition for the integral to be minimum? That is dou f by dou x plus dou d by dx of dou f by dou y plus d by dx of dou f by dou y dot is equal to 0 is the condition for minimum. The integral I or the integral t is minimum if dou f by dou y plus d by dx of dou f by dou y dot is equal to 0. Here what is f? F is equal to this much. Therefore, it contains only x and y dots. There is no term y. Therefore, dou f by dou y is equal to 0. We have to find dou f by dou y dot. We can find dou f by dou y dot, and we have to apply the equation. So, dou f by dou y dot is equal to dou by dou y dot of square root of 1 plus y dot square divided by 2gx. Dou by dou y dot of square root of 1 plus y dot square divided by 2gx, that is equal to, the denominator is a constant, with respect to y dot it is a constant, therefore we can write 1 by 2 root gx, 2gx Then differential of this one is equal to root x 1 by 2 root 1 plus y dot square into 2 y dot. Dou f by dou y dot is equal to 2 and 2 getting cancelled. This is dou f by dou y dot. Then we have to find d by dx of dou f by dou y dot. D by dx of this is equal to 0. That is the equation. The first term is equal to 0. Therefore, we have to find d by dx of dou f by dou y dot is equal to 0. That is d by dx of 1 by root 2gx 1 plus y dot square y dot is equal to 0. This is equal to 0. That means y dot divided by root 2gx into 1 plus y dot square is equal to constant. Since d by dx of this value is equal to 0, this value is equal to constant. Now we have to solve the problem to get the equation. On solving, the equation is somewhat complicated, and therefore we get the equation solution as y is equal to a cos inverse 1 minus x by a is a constant, minus 2ax minus x square all raised to 1 by 2. This is the equation we are getting. Right here, y is equal to a cos inverse 1 minus x by a minus this much. This is the solution of this equation. When we are differentiating this equation, we are getting y is equal to this much. A is a constant. If you can do the integration. Otherwise, you can get the equation just like this. This is the equation. This is the solution of Branch-Stockron problem. That is the problem of a body falling from the point 1 to 2 under the influence of gravity, and the equation for time taken. Minimum time taken is equal to this much. The equation for minimum time taken during such a motion is called Branch-Stockron problem, and the solution can be obtained by using the principle of technique of principle of variation principle, calculus of variation. Now, using the same principle, we can derive an equation that is called Euler Lagrange's differential equation. This we are going to derive. We have to derive Lagrange's equation as well as we have to derive Euler Lagrange differential equation. This is the Euler Lagrange differential equation. This is a equation based on the technique of calculus of variation. Using the same technique, same equation as we have done previously in order to find the minimum path or extremum path, we have used an equation in which dou f by dou y minus d by dx of dou f by dou y dot is equal to 0. This, using the same method, we can find the equation that is called Euler Lagrange's differential equation, and this equation is applicable for a function. As in the previous case, a function y is equal to a function of not only y, there are so many variables there, that is y1, y2, y3, etc. That is y1 of x, y2 of x, y3 of x, etc. Similarly, y1 dot, y2 dot, y3 dot, etc. comma x. This is the function. Here we have taken a function. In the previous case, we have taken a function of y dot and x. Here we have taken a function of y. It is not only a single function, that is yj, that is y1, y2, y3, etc. y etc. comma y1 dot, y2 dot, y3 dot, etc. and x. And another thing we have to consider is that here there are so many possible paths. We are taking, or actually we are coming to the minimum path. Before coming to the minimum path, there are so many possible paths. Therefore, we have to consider a variable r, a parameter alpha. Alpha is a parameter to consider while considering different paths for yj. For the jth component, we have to consider a parameter alpha for other paths, some comparative paths, not minimum path, but other paths. We have to consider a parameter alpha also. Therefore, we can write yj is equal to yj of x comma, not only x comma alpha. This equation can be written as, this equation actually is y is equal to a function of y1 of x comma alpha, y2 of x comma alpha, etc. y1 dot of x comma alpha, y2 dot of x comma alpha, etc. x this much. This is the actual equation. That is yj is equal to yj of x comma alpha, y1 is equal to y1 of x comma alpha, etc. So we can write the equation dou I by dou alpha is equal to, this is the total integral. We can write the integral as integral from 1 to 2. Total path can be represented as integral from 1 to 2 f of y dot x into dx. This is the equation. Therefore, we can write dou I by dou x is equal to dou I by dou x into dx. We can write this like this, is equal to, this equation can be integrated, taken just like this, dou I by dou x into dx. That is integral from 1 to 2. We can write sigma I is equal to, or j is equal to 1 to n dou f by dou y into dou f by dou yj into dou yj divided by dou alpha plus sigma j is equal to 1 to n dou f by dou yj dot divided by dou alpha into d alpha into dx. This is the equation. Dou I by dou x into dx is equal to, here we are multiplying, here we are taking the derivative dou I by dou alpha is not equal to dou x, dou I by dou alpha with respect to alpha here. Therefore, dou f by dou yj into dou yj by dou alpha plus dou f by dou yj dot dou yj by dou alpha into d alpha into dx. There is so many terms, 1, 2, 3, etc. y1, y2, y3, y4, etc. yj. Therefore, we are summing from j is equal to 1 to n like that. So, for this can be written as dou I by dou alpha into d alpha can be written as delta I. Delta I is equal to this much. And now we can integrate. Integrate the expression. Therefore, we get delta I is equal to integral from 1 to 2 sigma j is equal to 1 to n dou f by dou yj into dou yj divided by dou alpha into d alpha dx plus, now there is another term, integral from 1 to 2 sigma dou f by dou yj dot divided by dou alpha d alpha dx. That is to be integrated by applying the integration by parts. First function into integral of second minus integral of derivative of the first into integral of second. First function into integral of second, you know this equation, minus integral of derivative of the first into integral of second. Therefore, we can apply the same equation here, the same principle here. That is first function sigma j is equal to 1 to n. First function dou f by dou yj dot into integral of the second. We can write this in the reverse order. That is dou yj dot divided by dou alpha into dou alpha by dou f by dou yj dot into dou yj dot divided by dou alpha. Okay. First function into integral of second. What is the integral of second? Dou yj dot means dou by dou alpha of dou y by dou x. Therefore, integral of second means, this term means dou yj divided by dou alpha from 1 to 2. First function into integral of second minus integral of integration with respect to x. You see, it is integration with respect to x. Integral of derivative of the first, sigma j. Derivative of the first means d by dx of dou f by dou yj dot into integral of second. What is the integral of second? The same term, dou yj by dou alpha. Dou yj divided by dou alpha. All these things we have integrated with respect to x, therefore d alpha is here. Now in this equation, consider the second term. First term is this one, second term third one. Consider the second term. Here there is a limit to be applied, dou yj by dou alpha from 1 to 2. We know that the yj, the value of yj, variation of yj with respect to alpha is 0 at the two endpoints. There is no variation for yj with respect to alpha at the two endpoints. There is only variation at the points in between the endpoints. Therefore, dou yj by dou alpha at 1 and 2 is equal to 0. Therefore, there are only two terms, first term and second term. We can write delta I is equal to integral from 1 to 2 sigma j. First term we can write here dou yj by dou alpha. Here also dou yj by dou alpha, that can be taken as constant. Dou yj by dou alpha. Then here dou f by dou yj. Dou f by dou yj minus here d by dx of dou f by dou yj dot. D by dx of dou f by dou yj dot. Then there is d alpha and dx. Here integrating, here one dx also, here dx. This is the equation, and we are finding the equation for condition for minimum. When the path is the extremum path or minimum path, there is no variation for I. That is, for the extremum path, delta I is equal to 0. There is no variation to the value I integral. Therefore, it is equal to 0. Therefore, this term is equal to 0. For this term is equal to 0, this is not equal to 0. Therefore, we can consider this term inside the bracket is equal to 0. That is dou f by dou yj minus d by dx of dou f by dou yj dot is equal to 0. This equation is called Euler Lagrange differential equation. This is the Euler Lagrange equation, differential equation. This is a one-time equation in which we are taking values y is equal to y1, y2, y3, etc. And for the generalized problem, we can write dou f by dou yj minus d by dx of dou f by dou yj dot is equal to 0. This equation is called, it's a very important equation, this is called Euler Lagrange differential equation. This equation also is derived from the variational principle or from the technique of calculus of variation. Okay, from the same principle we have to derive Lagrange's equation also, that we will derive later. Therefore, this is another very important derivation we have to be studied in the case of Lagrangian formulation. Okay.